Alright, welcome to the NUPOC video study guide number 65. Let's go ahead and do another problem in our little viewer request detour here into waves and oscillations. Let's talk about deriving the period of a pendulum, because this is another really great fundamental problem in waves and oscillations and vibrations and all those things. And it's a great follow-up question to really look at a candidate's understanding of just basic like physics and differential equations and F equals ma and dynamics and all these things. And it's a type of problem that comes up a lot. Simple harmonic motion. It's a very practical problem as well. There's a lot of physical systems that that kind of fall into this category of this kind of oscillation and whatnot. So, anyways. When we talk about a pendulum, of course, we're talking about some mass, right? That's fixed. It's fixed to some anchor point by some either an inextensible string or a metal rod or something like that, right? And let's say it has length L, okay? And I go ahead and I displace that mass, right? Some distance from equilibrium, and this distance here is still L. And then I release it, and it flies back, and it goes through its equilibrium point, and ends up back here, right, on the other side of the equilibrium point by an equal distance to the original displacement, and it just oscillates back and forth like this, right? And so the period of that motion, right, period is just 2 pi root L over G. Like that, right? And that's just good to know. But how do we come up with this, right? That's kind of the question that we're trying to solve in this video, right? So let's go ahead and talk a little bit about this system. First of all, we have to make a number of assumptions, right? Like we already said that this connecting rod here has to be inextensible, right? We're not gonna stretch it, and there's no friction here at this joint, and there's no air resistance, and all these other things. And if all those things are true, then we'll get this motion here, and it will just oscillate forever. And of course, the interesting thing is the period of oscillation is totally independent of the mass, right? And that's kind of counterintuitive. You would think that maybe if it was a heavy mass, it might oscillate more slowly or something like that. But it's not true. It's only dependent on this length L and the gravitational constant G. And this is one of the ways. There's a video, in fact, of of astronauts on the moon and whatnot with a pendulum, and this is a way that you can effectively calculate the gravitational field that you're in, as if you have a pendulum of a known length, and you can set it oscillating and accurately measure its period of oscillation. Anyways, so we know that that we have L here and some mass, and we also have some angle theta here, right? Some angle theta that we displace this mass by to start the oscillation. And we have to assume that this angle theta is relatively small, so say less than about 15 or 20 degrees for our analysis to work and for this equation to hold. So let's take a look at how we would start coming up with this equation. Let's first look at the forces on this mass here once it's been displaced from equilibrium, right? So we have, I'm just drawing this force at the edge of the ball here, at the edge of the mass, just for the sake of simplicity. But of course, it does act at the center of mass. But anyways, we have some force mg down, right? And just like we do in these inclined plane sliding mass problems, we can break this down into two components, right? So we have some m, and by the way, this is of course theta as well. We have some mg cosine theta here. And here we have some mg sine theta force, right? So we can see right away that this mg sine theta force, right? This force is acting to pull the mass this way, back towards its equilibrium point. So this is the force that's really causing this mass to accelerate in this direction and causing the oscillation, right? So we can call this, let's call this Fr for the restoring force, okay? So we can say then that, well, before I say this, we have to know, and this is kind of the, something you have to know, just the trick to the problem that helps it fall apart, and fall apart very nicely. And you really have to know that for simple harmonic motion, for any simple harmonic oscillator, right, the restoring force is proportional to the linear displacement of the mass, let's say. So same thing in the spring mass system. The restoring force was proportional, right? It was kx, so it was proportional to the linear displacement. Here, though, the linear displacement is a little bit different. This length here, since we're moving along a circle, right, because this length L from this fixed point never changes, so that means we must be moving along a circular path. This distance here, from this point to this point, is L times theta, right? Because if you look at a circle and you have some theta here and some r, this distance, this arc length, that's r theta, right? Whereas this distance here, this is r sine theta. Anyways, so this is just something that you have to know. So for this, we can say, let's say that minus Fr is equal to minus k times L theta, because this is the linear displacement here. And when I wrote the alpha here, what I meant to say was that Fr is proportional. This means proportional to linear displacement. So we can just write an equality and write some constant k. And the negative signs are here because this restoring force is working in the negative direction. We're going to define moving towards the equilibrium point as the negative direction of acceleration, the negative direction for velocity, and the negative direction for force is going to be moving towards the equilibrium point. And we'll be on a, of course, you can already tell we've got, theta and L, so we're going to be in polar coordinates for this problem, right? And it'll make things much easier. All right, so let's go ahead and write out what the restoring force would be. So that would be minus mg sine theta, and now we can solve for k. So we can say that k equals, moving this minus, let's move the minus and the L and the theta to the other side, we'll get mg sine theta over L theta, right? And now here's where that small theta assumption comes in, because we can say that for small theta, sine theta is approximately theta, and I'm sure a lot of you have come across this, right? So if I have some circle, right, and my theta is reasonably small, right, this is theta, well that means, and this is r theta, but this, just inside it, is r sine theta. And of course the r's, we have the same r in both of them, so that doesn't matter. But the length is almost the same. And here we have a sine theta, and here we have a theta. So for small theta, sine theta is approximately theta, so we're going to use that here. So we're going to call this sine theta, we're going to call that theta, and then we'll cancel these two thetas. So we'll get that k is approximately equal to mg over L, right? So now let's go ahead and write out our F equals ma equation, right? Our acceleration equation for this mass, okay? And now you can see we're kind of getting onto the same path as we had in the previous video with the mass spring system, right? We're starting to do F equals ma, and we'll get a differential equation and all that stuff. So I can write now that the restoring force is equal to the mass times the acceleration, right? And so the restoring force, we said, is just, let's see, it would be k minus k times L theta, so that will be minus mg over L times L theta, right? That's the restoring force. This is Fr, right? Equals mass, right? times the acceleration. And again, we know acceleration is just the second derivative of the linear displacement, so that'll be d squared L theta dt squared. This is the linear displacement L theta, right? And so we can just bring the L out because L isn't varying with time, that's constant, so this will just be m times L times d squared theta dt squared, okay? So now let's rewrite it on this line to clean it up a bit. Let's cancel this L with this L. Let's cancel this M with this. Let's use this one all the way over here. We'll say this equals this, right? So we'll cancel this M with this M, and we'll move everything to one side of the equation, and we'll divide everything by L. And so what we will get is d squared theta dt squared. Let's see, plus g over L times theta equals 0, right? So now we just do the same procedure as we had in the last video, and we assume that theta, right, equals a cosine omega t plus b sine omega t, right? And then we go and we find out what theta prime equals, and we find out what theta double prime equals. I guess I could just write it out. This will just be minus omega a sine omega t, right? Plus omega b cosine omega t, and of course theta double prime, right, which is just our d squared theta dt squared, will equal minus omega squared a cosine omega t minus omega squared b sine omega t. And of course subbing in theta for theta, right, and theta double prime for the second derivative of theta here, and then moving all this g over L times theta to the other side of the equation. What we'll get is something like minus omega squared a cosine omega t, right, minus omega squared b sine omega t equals minus g over L times a cosine omega t minus g over L b sine omega t, right? And then doing the method of undetermined coefficients, we can say, right, that minus g over L must equal minus omega squared, so we can say that omega squared equals g over L, or omega equals root g over L, or plus minus root g over L, but we'll just say that it equals plus g over L, since negative frequency doesn't really have a physical meaning, and we're interested in the practical physical system here. And so then, of course, we also know that this equals 2 pi f, so we can say that f equals 1 over 2 pi root g over L, and of course we know that t is 1 over f, or f is 1 over t, so we can just invert that, and we'll say that t, the period of oscillation, is just 2 pi root L over g, which is what we started with. So that's just a quick walkthrough of a really great traditional fundamental problem in waves and oscillations. It's a great follow-up problem to asking what the formula is, and it really demonstrates, it brings together physics and dynamics and differential equations and all these things, and it's really a great problem to demonstrate a lot of knowledge.